Hey, AB Chem, I want to take a minute and introduce you to the term that is K in a very simple way. Now, we're not going to talk about all the ins and outs of Ks right now. We will talk about K later when we get to the equilibrium chapter. But for now, I just want to give you a functional view of K so that you can apply it in this lab. So this term K does have a real name. It's called the law of mass action. But what K really is a ratio. K is a ratio between products and reactants, usually measured in concentration or molarity. So the thing about K is the reason that we have K and we calculate K and the thing that we use K for is to tell us where a reaction stops. Now, you may be thinking, Mrs. Martins, the reaction stops when product is made, right? Well, not exactly. Reactions usually go forward to a certain point and then they stop. And they don't always stop when all the reactants are used up. For example, let's say you are making cookies with your 5-year-old, which I have lots of experience doing, thankfully. Okay, if you were making cookies with a professional baker, what you would do is you would make cookies until one of your reactants, one of your ingredients runs out. And then you have as many cookies as you possibly can have, right? That would be like a limiting reactant problem. If you are making cookies with your sweet little 5-year-old, on the other hand, you're going to make some cookies and then the 5-year-old is going to get distracted because there's a squirrel outside or there's bananas on the counter or she's wearing a super twirly dress. Something like that is going to distract her, and then she is not going to make cookies anymore. So you will have reactants left. You will have some products made, but your process has stopped. And actually, that is more truthful to what most chemical reactions look like. They go for a little bit, and then they stop in the middle and when there's reactants left and there's products left. And so we need a way of describing how far forward they go. And that is what K is. K describes how far a reaction goes because it tells us a relationship between products, which is your numerator, and reactants, which is your denominator. Okay, so for example, let's say we have A and it goes to B. If we start with 5 A's, molecules that look something like this, and 0 B's, and we use up 1 A, so therefore we form 1 B, and we're left with 4 A's, and we have 1 B that is made. Okay, I don't know how B gets made. Maybe A gets squashed. And so now we have a squashed A, which is what we're going to call B. Okay, so let's say this is our ending ratio for our reaction, right? So our K in this instance would be 1/4, which is 0.25. Okay, so K gives us a relationship between how much product we have made and how much reactant we have left. Now think, what would happen to K if this reaction went further and made more B? Would K increase or would K decrease? Okay, let's find out. So let's say we start with 5A and 0B and we squash 2 of our A's, so we get 2 little B pancakes. Oh, yes, we're going to make 2, so we have 3 left, and we have 2 over here. So K in this instance would be 2/3, so 0.67. So notice when we have more product and we lose more reactants, our numerator goes up, our denominator goes down, and our K gets bigger. So the more products we make, or the further our reaction goes to completion, the bigger the K is going to be. So let me give you an example of something like this. All right. In your book, we have MgCO3 and we have CaCO3. Okay, so what we're dealing with in gravimetric analysis is salts that dissolve in water. So salts that fall apart into their ions in water. So this happens to both of these things. But these are not soluble salts. These are slightly soluble salts. So the question is, how much do they fall apart in water? That's why our K has that little SP at that bottom. That SP is indicating that it's a solubility product. So it's describing the solubility of a salt. You can have lots of different Ks. You can have a Ka that describes acid dissociation. You can have a Kb that dissolves base dissociation in water. So this one is going to be KSP because we're talking about the solubility of salts in water. So again, we want to know how much do these salts dissolve? How far do these salts fall apart and turn into ions? So the Ks for both of these are given. The K for magnesium carbonate is 3.5 times 10 to the negative 8th. The K for calcium carbonate is 2.8 times 10 to the negative 9th. Okay, so the question is, can we look at the K and can you tell me which one is more soluble or which one will produce more ions in solution? So the first question you should ask yourself is, which of these numbers is bigger? That number is bigger. So that means that the products are going to be greater than the reactants when compared to the products versus reactants for calcium carbonate. So the numerator is greater than the denominator for magnesium carbonate. The numerator of magnesium carbonate is greater than the numerator of calcium carbonate, or the denominator is smaller, either way. So since this one has a bigger K, the product to reactant ratio for magnesium carbonate is more towards the products than it is for calcium carbonate. So we say magnesium carbonate is more soluble. It's going to dissolve into more ions when compared to calcium carbonate. Now, there are a couple catches with Ks. You can't always look at Ks and compare salts directly, but we'll talk about some of those details once we get into equilibrium and we look at the law of mass action more closely. For now, this is how we'll use it in this lab, and you can look at the Ks and rank the solubilities of the salt based on which one has a larger ratio. Okay, let me know if you have questions. Take a look at that pre-lab and we'll talk about this together.